Good morning, ladies and gentlemen. Welcome back to the one-week international online faculty development program on recent trends and advancements in information technology, organized by Department of Computer Applications, FISAT. We are moving on to the first session for the day on sequential data processing using LSTM. I'm extremely happy to introduce the speaker for the session, Dr. Sabu M K, Associate Professor and Head, Department of Computer Applications, CUSAT. He has several research publications in his credit, including international and national journals and conference proceedings. He has been honored twice as a Best Performing Teacher Award and has got a grant from UGC to visit Switzerland for presenting a research paper in Second International Conference on Artificial Intelligence and Applications. He has chaired many sessions, which includes IEEE international conferences on circuits and systems in digital enterprise technology, 7th National Conference on Indian Language Computing, IEEE International Conference on Data Mining and Advanced Computing, and also coordinated many seminars, workshops, and symposiums. On behalf of all of you present over here, I welcome I welcome Mr. Sabu M K to the session. Over to you, sir.
Am I audible?
Yes, sir. Yes, sir.
My slides visible to you?
Yes,
Yes,
sir.
sir. Yes, sir. It's visible.
Okay, okay. Okay. Good morning, all of you.
Excuse me, sir. The presentation
Yes.
is not there. Presentation is not there. It was closed.
Yes, it's visible now, sir.
Okay, okay. Thank you.
Okay.
At the outset, I extend my sincere thanks to the Department of Computer Applications, Federal Institute of Science and Technology, especially the head of the department, Sandosh sir, and my students working as faculty members in the department for inviting me to participate in this 5-day workshop on recent trends and advancements in information technology as a resource person. And in this pandemic situation, I would like to share with you some very basic concepts of machine learning, especially long short-term memory through this online platform. And due to the limited time allotted to me, we can move directly to the topic. And the topic of today's presentation is sequential data processing using LSTM. And these are the topics I'm going to discuss in this session. As a first point, I would like to introduce the concept of recurrent neural networks. After that, we can discuss the difference between recurrent neural networks and feed-forward neural networks. Now we can move on to architecture of recurrent neural networks. Then we can move on to the architecture of long short-term memory. And at last, we can implement the concept of LSTM with the help of Keras functionality available in Python by taking a very simple problem. And this is the agenda of my presentation. And all of you know uh, what is the concept of neural networks and what is the importance of that neural networks in today's research. And when we compare the difference between ordinary neural networks and the recurrent neural networks, there is always a significant difference between the architecture of these two models. And when we consider human beings, humans don't start their thinking from scratch every second. And we understand things based on the past experience. And the best example is the decision regarding the items for tomorrow's breakfast is mainly based on what items are included in today's breakfast and previous day's breakfast, and based on that we can take the decision regarding the next day's breakfast items. But traditional neural networks can't do this, and it seems like a major shortcoming. And when we come to recurrent neural networks address this issue. That means we can consider our past experiences for decision making. And the recurrent neural networks are nothing but they are neural networks with loops in them and allowing information to persist. That means it is possible to consider previous experiences to take a decision regarding or for decision making problems. A recurrent neural network looks very much like a feed-forward neural network. Feed-forward neural network or simply neural network. I think all of you know the architecture of a simple neural network. And what are the various components contained in a perceptron model? And the components are nothing but some inputs are there, some weights are there, a summation processor or summation operator is there, an activation function is there, and this activation function produces an output. Hello.
Yes, sir, you're audible.
Oh. Activation function generates the outputs. But in the case of a recurrent neural networks, the construction of a recurrent neural network is very much like a feed-forward neural network, except it has connections pointing backward. Connections pointing backward means the previous computations outcome that can be considered for processing the present input, and that is the advantage of using recurrent neural networks. And consider the simplest possible recurrent neural network composed of just one neuron receiving inputs, producing an output, and sending output back to itself in order to use it while processing the next input as shown in the slide. But this is the general architecture. This is the current input. And at the time of processing this current input, the just previous output is also taken into consideration. And when we expand that construction, and this is the expanded form of the recurrent neural network. But here, when we consider the is actually a the name of the topic I have selected is sequential, the processing of sequential data. I think all of you know what is actually the sequential data. Sequential data is nothing but there is always a one-to-one mapping between the set of integers and the set of data items. That means every data item is associated with a particular integer number. That is, and these integer numbers are consecutive integer numbers. That means, for example, x1, that is the first data item, x2, that is the second data item. That type of an enumeration is there in a sequential data, or it can be considered as a time series data. That means every data item is associated with a timestamp. So here, when we consider xt minus 1, and when we process this xt minus 1, the output obtained from the just previous iteration, that is xt minus 4, that is also taken into consideration. Then by considering that, we can generate the output yt minus 3. And similarly, this yt minus 3 becomes an input of xt minus 2. And yt minus 2 becomes an input of xt minus 1, and so on. This type of processing is always happened in a recurrent neural network. So this yt minus 2 at the time of processing xt minus 1, or yt minus 1 at the time of processing xt can be considered as the previous output obtained from the just previous operation. And based on these two inputs, we can take the decision regarding that is yt. Okay, that is the general concept. And at each time step t, and this time step can be considered as a frame. At each time frame t, the recurrent neuron receives the inputs x of t, that is the current input, as well as its own output from the previous time step, and that output can be symbolically represented as yt minus 1. And this is the unrolled, this diagram is the unrolled architecture of the recurrent neural network. So this is x, that is the current input, and we have one more input, and that is the output from the previous operation, and that output is actually represented by using y. Okay, and each recurrent neuron has two sets of weights. One for the input x of t, that is the current input, and that weight can be represented as wx, and the other for the output of the previous time step yt minus 1, because here we have two different inputs, and the weights can be represented as weights corresponding to yt minus 1 can be represented as wy, and the output of a single recurrent neuron, and that can be computed by using a mathematical expression, and that mathematical expression is nothing but yt is equal to phi of xt transpose wx plus yt minus 1 transpose wy plus d. This is a matrix operation. These are two matrices. These are also two matrices, because when we consider the concept of a neuron, and inside that neuron we have a summation operator, and that summation operator is responsible for computing the weighted sum of inputs. So this is the weighted sum of the first input, this is the weighted sum of the second input, and this is a bias term. I think all of you are familiar with the equation of a straight line and all. And here b is the bias term, and phi is nothing but the activation function. Every neuron is associated with, in neural network, every neuron is associated with an activation function, and here that activation function can be represented as phi. A number of different type of activation functions are there: sigmoid activation function, ReLU activation function, Tanach activation function, etc., etc. So the computation, this is the vector representation of the computation. Yt is equal to phi of xtwx plus yt minus 1 wy plus b. As a matrix operation, it can be simply, we can represent the mathematical equation in this format: xtyt minus 1, that is a matrix, w is another matrix, that is wx wy weight matrix plus b. And this is the mathematical concept of the recurrent neural network. Then now we have to understand what is actually the training of a recurrent neural network. We can think a recurrent neural network as a layered feed-forward net with shared weights, and then train the feed-forward net with weight constraints. But here we have a number of weight values. When we consider the input xt, we have some weight values. Yt minus 1, that is the previous output, we have some weight values, and the updation of these weight values are actually termed as training. And in this case, in the case of RNN, backpropagation through time, or BPTT, is the training algorithm used to update weights in recurrent neural networks. And in the case of ordinary neural networks, I think we are familiar with the stochastic gradient descent, and that is the basic methodology used for training the neural networks, stochastic gradient descent. And with the help of this stochastic gradient descent, we can update the weights. And here, derivative becomes a very important component. And you know what is if you consider the function y is equal to f of x, its derivative can be represented as dy by dx. And this dy by dx, or the gradient plays a very important role in updating the weights or training the neural network. And backpropagation through time is normally applied to sequence data like time series, and it can be explained with the help of this particular algorithm. That is, present a sequence of time steps of input and output pairs to the network. That means, in the case of a recurrent neural network, the input is always a time series data or a sequential data. Then after that, we can unroll the network, then calculate and accumulate errors across each time step. Each time step, we can calculate the current prediction. Actual prediction is always available in our custody, and with the help of the actual prediction and the generated output, we can compute the error, and this error can be back propagated for each time frame. And so we can roll up the network and update the weights. Update the weights means for each time frame we can modify the weight values, and this process is repeated until the network stabilizes. Until the network means in this case the recurrent neural network, until that recurrent neural network as a when that neural network becomes stabilized, then we can stop the process, and this process continued for each time frame. And that is what is actually happening inside the recurrent neural network. And in order to understand that particular concept, we can consider this particular architecture. But here, x0, x1, x2, these are the inputs at each time step, and the corresponding y values also there. Then here, this is the predicted value. Actual value is available in our data set. Then by considering the actual value and the predicted value, we can compute the error. At each time frame, we can compute the error, and that error is back propagated for updating the weights. And the process is actually known as back propagation through time. Now we can move on to the long short-term memory, that is LSTM. And the LSTM is actually a modification of the recurrent neural network. So in LSTM network, that is actually a recurrent neural network that is trained using backpropagation through time and overcomes the vanishing gradient problem. Again, I think all of you know what is actually the vanishing gradient problem. As I said earlier, the weight updation is mainly based on gradients. Gradient means dy by dx. For example, if you consider y is equal to x squared, then what is dy by dx in the when we consider the first derivative of that function x squared, we get 2x. Okay, and when we differentiate once again, we get a constant value, that 2. Once again, when we differentiate, the differential coefficient of a constant, that is always 0. That means after the elapsing time, the gradient will vanish in some situations. And this is a very serious problem in the case of recurrent neural networks. And this problem can be taken into consideration while constructing the long short-term memory. So this problem can be minimized or eliminated in this particular construct, and that construct is long short-term memory. And with the help of this long short-term memory, it is possible to create large recurrent networks. Any number of recurrent networks can be generated with the help of LSTM. And instead of neurons, LSTM networks have memory blocks that are connected through layers. And that is the main difference between the recurrent neural networks and the LSTM. Then when we consider recurrent neural networks, some neural network components are there inside the recurrent neural network. But when we consider LSTM, and in addition to the conventional neural network components, this LSTM has some memory blocks also. So an LSTM block, when we consider an LSTM block has classical neuron components. Classical neuron components like inputs, weights, summation operator, activation function, etc. All these components are there. Plus some memory for the recent sequences. In order to store the recent sequences, the status of the recent sequences, we can use some memory components also in LSTM. That is, a block contains gates that manage the block state and output. That means what information we have to store in the LSTM cell, and that is actually decided by some gates. Gate networks are there. A block contains gates that manage the block state and output. A block operates upon an input sequence, and each gate within a block uses the sigmoid activation units to control. And this statement is very important. A block operates upon an input sequence, that is the input of that particular block, and each gate within a block uses the sigmoid activation function. I think all of you are all of you know the mathematical equation of a sigmoid activation function, 1 divided by 1 plus e raised to minus x. That is the mathematical equation of a sigmoid function. And what is the speciality of this sigmoid activation function? We can very easily compute the differential coefficient, and that is the speciality of this sigmoid activation function. And the differential coefficient is nothing but a very simple mathematical equation, and that mathematical equation is actually x into 1 minus x. And that is the reason why we use sigmoid activation function for processing the data in neural networks. So here the sigmoid activation function is used to control whether these gates are triggered or not. Then whether that particular gate we have to trigger or not, that can be controlled with the help of the sigmoid activation function. And another advantage is any change in the state of the block, what information we have to store, and that can be decided with the help of this sigmoid activation function. Or another advantage is add any new information and allow this new information to flow through the block. That is what information we have to store in that particular memory block, that can also be decided with the help of this sigmoid activation function. So this particular information is very important in the case of long short-term memory. But here, when we consider a block of an LSTM, a block operates upon an input sequence, that is the input, and each gate, every LSTM block contains some gates. Each gate within a block uses the sigmoid activation function, activation units, to control whether these gates are triggered or not. Any change in the state of the block, add any new information, and allow this new information to flow through the block. All these activities can be controlled with the help of various gates contained in the LSTM block, and inside that gate we can make use of a sigmoid activation function to control. And all these activities are performed conditionally. And mainly there are three types of gates within a unit. The first gate, and that is known as the forget gate. And this forget gate conditionally decides what information to throw away from the block. Some informations are not needed for the data processing. That type of informations we can eliminate, and that can be done with the help of a forget gate. Then another gate is known as the input gate, and this input gate conditionally decides which values from the input is used to update the memory state. That is, from the input, what type of information we have to extract to store in memory, and that is actually decided by the input gate. The other gate is known as the output gate, and this output gate conditionally decides what to output or generate based on the input, current input, and the memory of the status of the memory or the content of the memory contained in that block. And that is the functionality of the output gate. So the output of an LSTM cell, that is actually decided by the output gate. And each unit is like a mini state machine where the gates of the units have weights. Every gates have some weights, and that are learned during the training process. As I said earlier, back propagation through time. This is the learning algorithm used in the case of long short-term memory. During that training period, these weights can be updated. These weights can be updated. And with the help of these weights, we can decide what information we have to preserve in the memory cell, what information we have to throw away, and what information we have to output. All these decisions we can take by considering these weight values. And this is the general architecture of a long short-term memory. So all these are fully connected layers, as in the case of our feed forward neural networks. And here this operation represents element wise multiplication, and this operation represents the addition operation, and this is the logistic function or sigmoid function, and tan h represents this represents the tan h function. So here these are the different gates: forget gate, input gate, output gate, and how these gates will operate within that particular LSTM cell, and that we can discuss in the next few slides. Anyway, you just go through the general architecture of this LSTM, and what is T minus 1 h, T minus 1 xt. Xt is the current input, and h of T minus 1, that represents the previous output, and these two informations are very important for an LSTM cell. And here the LSTM cell looks exactly like a regular cell, except that its state is split into two vectors, h of t and c of t. And here c stands for a cell, and that means that cell actually represents some memory. We can consider h of t as the short-term state and c of t as the long-term state. Okay, over here the memory can be divided into two. A short-term memory is there and a long-term memory is there, and the short-term memory can be represented as h of t, and the long-term memory can be represented as e of t. And the key idea is that the network can learn what to store in the long-term state, what to throw away, and what to read from it. And that is the main idea behind an LSTM cell. That means an LSTM, the idea used in an LSTM cell is that the network can learn what to store in the long-term state. That is, in a long-term memory, what information we have to store, that we can decide, and what to throw away. Some unwanted information is there, and those type of unwanted information we can throw away from the LSTM cell, and what to read from it, what actually we have to output. And all these informations can be done with the help of the various gates available in the long short-term memory. And the long-term state CT minus 1 traverses the network from left to right. It first goes through a forget gate, dropping some memories, and then it adds some new memories via the addition operation. And this is very clearly visible in the architecture. CT minus 1 flows from left to right. Okay, and during that flow, it throw away some informations, unwanted informations, with the help of the forget gate, and add some new information obtained from the present input and h of t minus 1. Then it filtered with the help of a tanh function. It filter out some informations, and with the help of the output gate, the filter out information can be modified, and it can be output as the short-term state, and it becomes the current state of that LSTM cell. And here, this represents the long-term information we have to store inside that particular cell, and this becomes available for the next computation. Okay, that is what is actually happening inside the LSTM cell. That is a very beautiful concept. The long-term state CT minus 1 traverses the network from left to right. It first goes through a forget gate, dropping some memories, and then it adds some new memories via the addition operation. That means at each time step, some memories are dropped and some memories are added. And after the addition operation, the long-term state is copied and passed through the tanh function. As I said earlier, and then the result is filtered by the output gate. And that, as a filtering operation, we can generate the actual output of that particular cell. And at the same time, we can produce a short-term state, that is h of t. That is the output, and h of t is always same, and that is evident in the architecture. That is here h of t and y of t. H of t represents the short-term state, and that short-term state becomes the output of the current LSTM cell, and this becomes an input to the next LSTM cell for processing. This produces the short-term state h of t. H of t is equal to the cell's output for this time step, and that output can be represented as yt. So here, working of these gates are as follows. We can conclude the working of these gates in this way. The main layer is one that outputs g of t. The main layer is the one that outputs g of t. This is the output. But here, this is the main layer. And with the help of the tanh function, we can generate the output g of t, and the output is generated by considering x of t and h of t minus 1. This is a very relevant information, and this relevant information is added into the long-term state. And it is responsible for analyzing the current input xt and the previous, that is short-term state h of t minus 1, that is the previous output. And when we consider a recurrent neural network, these are the only two inputs in the recurrent neural network. No other gate controllers are available in the case of recurrent neural network. That means there is no information regarding the long-term state. Okay, but here we have only some short memory, that is the information obtained from the just previous output. So in the basic cell, that is in RNN, there is nothing else than this layer. Means the only layer is this fully connected layer. That is the component of a recurrent neural network. All the other components are not available in the case of a recurrent neural network. That is the main difference between the LSTM and the recurrent neural network. So in LSTM, this layer output is partially stored in the long-term state. Long-term state means from this output we can eliminate some unwanted information. Only relevant information we can store in the long-term state, and that is the speciality of the long short-term memory. The three other layers are gate controllers. The three other layers, in addition to g of t, three other layers are also there. These are gate controllers. Their outputs are fed to element wise multiplication operations. And element wise multiplication, I think all of you know the concept of element wise multiplications. And using the element wise multiplications, if the output is 0, if the output of that element wise multiplication is 0, we can close the gate. That is, it is not possible to open that gate. Means it is not possible to transfer any information through that particular gate. And if the output is 1, they open it. Open it means we can flow or we can transfer the information. Okay, and that type of a controlling operation can be done with the help of the element wise multiplication operations. And when we come to the forget gate, that is the forget gate controlled by f of t controls which parts of the long term state should be raised. That is the long term state that is actually obtained from the previous operation, and from that previous operation what information we have to throw away for the current operation, and that is actually controlled by f of t. Then the input gate that is controlled by I of t controls which parts of g of t should be added to the long term state. That means g of t that is actually calculated from the just previous short term state and the current input. And here what are the necessary information we have to store from g of t to the long term state, and that is actually decided by the input gate. And the output gate that is controlled by OT controls which parts of the long term state should be read and output at this time step, and it is represented as h of t and y of t. That means from the long term state what information we have to produce as the output of that LSTM cell, and that is actually decided by or controlled by O of t. So these three gate controllers are very important in the case of LSTM. These gate controllers actually decides the status of the memory cell, what information we have to throw away, what information we have to read, and what information we have to add into the long-term state. These type of operations are actually controlled by these three gate controllers. So an LSTM cell can learn how to recognize an important input. That is the role of the input gate. And from the current input and the previous output, what information we have to recognize. And that is actually decided by the input gate. And then store it in the long-term state. After taking that decision, it is maintained or it is stored in the long-term state. Okay. Then next is learn to preserve it for as long as it is needed, and that is the role of the forget gate. And from the long-term state, what information we have to throw away, because some unwanted information is there, and all those type of unwanted information we can throw away from the long-term state with the help of the forget gate. And learn to extract it whenever it is needed. That means from the long-term state, what information we have to produce as output, and that is actually that is the role of the output gates. An LSTM cell can learn to recognize an important input, and that is the role of input gate. Store it in the long-term state. Learn to preserve it for as long as it is needed, whether the information available in the long-term state is needed for the present processing or not. And that means some informations are unwanted. That type of informations we can throw away, and with the help of forget gate, and that is the role of the forget gate. And learn to extract the necessary information whenever it is needed, and that is the output of the or current output of that particular LSTM cell, and that is actually generated by the output gate. And these are some mathematical computations corresponding to various gate controllers and the long-term state, the short-term state, and the current output of the LSTM. I don't like to go much deep into this particular mathematical computations, and all these are vector computations. And here sigma represents the sigmoid activation function, and tan h, that is another activation function. These are the two different very important activation functions involved in the computation of long short-term memory, and these activation functions are very, very important and very significant activation functions, because with the help of the inclusion of this tan h is nothing but I already mentioned about some vanishing gradient problem, and that vanishing gradient problem can be handled very effectively with the help of the tangent function. That is the significance of this hyperbolic tangent function. And all these are some basic concepts. And if you are interested in understanding the mathematical concept of long short-term memory, that means various gate controllers, various connector layers, etc., etc. You just search for these mathematical expressions, and all these are vector operations. And here WXI, WXF, WXO, WXG, and all these are some weight matrices. And for each of the four layers, for their connection to the input vector Xi. That means when we consider a particular LSTM cell, Xi, that is the current input, and this when we consider this current input, some weight matrices are always associated with this current input and the various gate controllers. And these weight matrices are WXI, that is the input gate, WXF associated with the forget gate, WXO, that is the output gate, and WXG for computing G. These are the weight matrices. And similarly, another important information or input is the output from the just previous memory cell. And in order to process that input, we need some weight values. WHI, WHF, WHO, WHG, and these are the weights matrices of each of the four layers for their connection to the previous short-term state. And short-term state HT-1, this HT-1 is obtained from the previous LSTM cell, and it becomes an input for the current LSTM cell. And in order to process this HT-1, we need some weight values, and these are the weight values. And BI, BF, BO, BG are the bias terms for each of the four layers. And all these, since all these operations are matrix operations, and in order to perform matrix operations very efficiently, Python provides a functionality which is known as TensorFlow. And this TensorFlow, tensors means high dimensional vectors. TensorFlow initializes BF to a vector full of ones instead of zeros. And this prevents everything will be zero at the beginning of the training. Here TensorFlow initializes BF to a vector full of ones. That is the initialization. Otherwise, in the initialization itself, all the computations becomes zero. So here the TensorFlow automatically initializes BF to a vector full of ones. And now I am going to explain the concept of LSTM with the help of a very simple real life problem. And here the problem is actually the international airline passengers prediction problem. And this is very simple. And the problem is nothing but, given an year and a month, the task is to predict the number of international airline passengers in units of thousands. And this is the problem. We have to predict how many passengers will travel the next year based on the current status of the traveling of the passengers. And for that, a data set is available, and the data ranges from January 1949 to December 1960, or 12 years, with 144 observations. 144 observations are there. And this is the snapshot of the data set available in my system. That is here the first represents the month and the year. 1949 January, 112,000 passengers traveled during that period. Okay, then 194902 is February. In the month of February, 118, March 132, April 129, May 121, and so on. So here in the data set, the data from January 1949 to December 1960 data is available. Okay, and we can load this data set easily using the pandas library. I'm going to discuss the program by using Python and Keras library. You can try this program because in a Jupyter notebook or Google Colab, you can just type all the program contents and just verify whether how the LSTM will work to produce the output. And in this case, we are not interested in the date, given that each observation is separated by the same interval of 1 month, because this is a sequential data. This is a sequential data. Therefore, we load the data set. When we load the data set, we can exclude the first column. The date column I just eliminated at the while loading the data. While loading the data, date value is eliminated. Once loaded, we can easily plot the whole data set to understand the or to visualize the pattern of that particular data. We can just visualize the data set, and that can be done with the help of these program segments. For example, important pandas. I think all of you are familiar with Python and all. Pandas means there is a data structure available in Python. Pandas and NumPy. These are two very efficient data structures available in Python. And the main difference between the pandas and NumPy is that NumPy actually represents the matrix form. Only numeric values are there. And in the case of pandas, each column can be labeled, and each row can be labeled there. So labeled rows and columns, that is possible, as in the case of our in relational database management system. If you consider the concept of a table, all the columns are labeled, right? And that type of a concept is there in pandas. Then import matplotlib.pyplot as PLT. This is another library needed for plot the data set, or plot the results, or plot the graph. And we need some functionalities, and all these functionalities are already available in Python. And the library needed for that plotting operation is matplotlib. Then in order to load the data set, we can use this particular functionality, read CSV, because my data set is in CSV format, that is comma separated value format. Okay, and in order to read that CSV, we have a functionality, dedicated functionality, and this functionality is a part of pandas. So in order to access that functionality, we can make use of pandas.readCSV. Then this is the name of the file, airlinepassengers.csv. And here just I mentioned only the name of the file, whether if this particular CSV file is loaded in a particular directory, we have to, along with this file name, we have to specify the complete path. We have to specify that complete path. So airlinepassengers.csv, use columns 1. Use columns 1 means I just try to eliminate the date column. We don't want the date because it's a sequential data. So all the columns are labeled from 0, 1, 2, 3, etc. So 0, column number 0, that is not needed. We need only the column number 1. So you just specify the syntax, use columns 1. And engine, that is Python, and using a Python framework, I'm going to process this data, and that is the reason why we specify engine is equal to Python. Some other engines are also there. Yeah. Then pipe plt.plot. Here plt, that is an object of matplotlib. Okay, then in order to plot the data set, we can use this functionality plot, and with the help of this object plt.plot data set. Then after that, you just in order to visible that particular plot, you can use plt.show. And when we analyze that data, when we analyze when we plot the data, we can see an upward trend in the data set over time. And you can also see some periodicity to the data set. And this is the visualization of the data available in my hands. Okay, but here we can use that upward trend and the periodicity, and that is visible in this particular graph. And plotting this graph, and that is very important. Then only we can understand what type of data processing technique we have to use. And what type of probabilistic distributions we have to apply for processing the data, and so on. In order to take the decision regarding all these things, first of all, we have to plot the data. And it is a good practice to investigate various data pre-processing techniques to rescale the data and to make it stationary. Some pre-processing techniques are very important for accelerating the performance of the model. And here, I'm going to use this LSTM network as a regression model, and we can phrase the problem as a regression problem here, because we are going to predict a numeric value, and that type of problems are actually known as regression problems. Some other problems are also there, and that problems are actually known as classification problems or clustering problems, and so on. And that is from machine learning. Okay, and that is given the number of passengers in units of thousands in this month, what is the number of passengers next month? That means when we input current month passengers details, it will predict and in the next month how many passengers will travel. Okay, and that type of a the decision we can take by using this particular LSTM network. But that is this is the problem. That is, given the number of passengers in this month, what is the number of passengers in the next month? And that type of a decision we are going to take using this particular LSTM network. Then again, in order to construct the model and process the model, we need some other functionalities, and these functionalities are already available in the Python, and you just import these functionalities to our program. And for that, first is import this NumPy library. NumPy means, as I said earlier, some metrics of NumPy can be considered as a data structure, and metrics type data structure is there. A number of different functionalities are there to process the metrics or the NumPy array, and all these functionalities are available or accessible through this particular library. So we have to import that library into our program, import NumPy, then import matplotlib.pyplot splt, as I said earlier, import pandas, import math. Since all these libraries are already included in our program, there is no need of include these libraries once again. Then from keras.models, import sequential. And here, Keras is a very important library available in Python for creating neural networks. Any type of neural networks can be generated with the help of the Keras library. And mainly, the neural networks can be classified into two in Keras: sequential neural networks and functional neural networks. And here I am going to use the sequential neural networks. That means, and here when we discuss the concept of a deep neural network, and in the case of deep neural network, we have an input layer, two or more hidden layers, and an output layer. And all these layers are connected sequentially in the case of sequential neural network model. And here I am going to use a sequential model. Other model is functional, and the functional model is a little bit flexible model. And in the case of functional model, at each layer we have to explicitly specify the input and the output of that particular layer. But in the case of sequential model, there is no need of explicitly specifying the input and the output, because this is a sequential. From the first layer, it goes to the control, goes to second, then from second to third, then third to fourth, and so on. And finally it goes to the output layer, and that type of a construct is there in the case of the sequential data model. So we have to include that model into our program. For that, from keras.models, import sequential. In some systems, if we use the latest TensorFlow model, there is a slight change in this particular statement. From Keras, instead of using from Keras, we have to use from TensorFlow.keras.models import sequential. Actually, this program I just created using an old version of TensorFlow, and that is the reason why this particular statement exists in this program. The latest version, if you use the latest version, instead of from Keras, we have to use from TensorFlow.keras.models import sequential. Similarly, from TensorFlow.keras.layers import dense. That is, dense means hidden layer. Then in order to add, we can add any time, a hidden layer can be added into the model at any time, and with the help of this functionality, that is dense. And from keras.layers import LSTM, we are going to use the LSTM model. And from sklearn, scikit-learn, pre-processing, import min-max scaler. Here I am going to use a pre-processing operation. From sklearn.metrics, import mean squared error, and this is for this is a metric for evaluating the performance of the model. And these are some important libraries. And before we do anything, it is a good idea to fix the random number seed to ensure our results are reproducible. Because here, as I said earlier, a number of different matrices, arrays, a number of different data structures are there in the at the time of constructing the LSTM model. And as a first step of the process, we have to initialize all these matrices, with the help of some random numbers. And these random numbers are actually generated with the help of a seed number for reproducibility. Otherwise, it is not possible to predict what random number is going to use for initializing that particular matrix or initializing that particular array. And in order to reproduce all these numbers for each execution of the program, we have to generate these random numbers with the help of a seed number. Seed value. Okay, a random number generating function, a number of different random number generating functions are there. You just analyze the nature of these random number generating functions. Then what is the role of seed number in that random number generating functions? And you can verify that concept. Okay. Then as I said earlier, we can load the data set. This statement I already explained in the previous slide. Then here, as a data frame, we can load the CSV file. And that data frame is available in this user defined object, that is data frame. And from that data frame, we can access the values, that is the actual values. And these values can be stored in a matrix, and that matrix is data set. This is also user defined object. Data set is equal to data frame dot values. Data frame is in that pandas format, data frame format. And from that data frame format, we can access the values with the help of dot values. And now we can store the values in a matrix, that is a two-dimensional array, and the name of that two-dimensional array is nothing but data set. Then next we can convert all the different numbers as floating point numbers, because most of the time LSTM cell or any neural network related architecture works with floating point numbers. So we can convert all these numbers as floating point numbers by using a functionality that is a dataset dot as type float. Okay, so now the dataset contains a number of values, and all these values are floating point numbers. And LSTMs are sensitive to the scale of the input data, specifically when the sigmoid or TANH activation functions are used. And by default, sigmoid activation function is used in an LSTM. And the speciality of the sigmoid activation function is that its value ranges from 0 to 1. That means the sigmoid activation function always returns a value lies in between 0 and 1. So we have to convert all the data values or map all those data values into a data value lies in that particular range. And that is a better option for efficient data processing. So LSTMs are sensitive to the scale of the input data, specifically when the sigmoid or TANH activation functions are used. So it can be a good practice to rescale the data to the range 0 to 1, and this processing, this operation is actually known as normalizing. So we map the actual data into another domain, and in that domain all the data values ranges from 0 to 1, and that process is actually known as normalizing. And we can easily normalize the data set using the min-max scalar pre-processing class from the scikit-learn library. And the scikit-learn library already have a particular facility for this particular normalization, and that facility is actually known as min-max scalar. And how we can normalize the data set? Using this these two statements, we can normalize the data. Scalar is equal to, we have to define an object. What type of object? Min-max scalar. Feature range is equal to 0 to 1. That means by considering that particular range, we can define a min-max scalar, and that min-max scalar functionality is now defined using a scalar. Okay, any name you can specify here. Then using that particular object, we can normalize the data. Our data set can be normalized with the help of this particular statement. Data set is equal to scalar dot fit transform. And this is a dedicated functionality available in this scikit-learn library, that is in the min-max scalar, that is fit transform data set. That means when this particular statement is executed, all the data values are converted directly into this particular domain, that is in between 0 and 1. Okay, so that type of, that is a data pre-processing operation, and that pre-processing operation is actually known as normalization. Next we can split the ordered data set into train and test data sets, and the code below calculates the index of the split point where we have to split the data, and separates the data into the training data and test data. And in this particular example, for training, that is in order to for learning purpose, we reserve 60% of the observations, or from among the total data, 60% of the data is reserved for training. That is in order to extract the patterns, or in order to learn the properties of the data, we use 67% of the data, and for the remaining 33% is used for testing. Testing means for evaluating the performance of the model. For performance, measuring the performance of the model, we can reserve 33% of the data. And in this example, this is the procedure I have applied for creating the training data and test data. Train size. First of all, we can compute the train size. So integer part of length of data set. Length of data set actually returns how many instances are there. How many instances are there into 0.667. That is 67%. Okay, and based on that, we can compute that index value, and that index value can be stored in train size. Then test size. Test size is length of data set minus train size. So 100 different elements are there. So 60%, for example, 0 to 60, and that may be the train size, and 61 to 40, that may be the test size in that case. But here 67%, and corresponding to that 67%, we have an index value, and that index value is now available in train size, and the remaining is reserved for test. So test size can be computed like length of data set minus train size. Then the actual data we can now split into two, that is training data set and the test data set, with the help of this functionality. There is a data set of 0 to train size, all columns, because here the data set can be considered as a matrix, and 0 to train size, all rows, from 0 to train size with all columns, and all these instances are stored in train. So train becomes the training data, and the remaining, that is data set train size to length of data set, all columns, that is now available in test. So we can divide the total data into training data and the test data, and you just print the length of the training data, length of the test data, and that is only for visualization purpose. Now, write a simple function to convert our single column data into a two column data set. Okay, and this is very important because LSTM can be considered as a supervised machine learning algorithm. Hence, to work with this model, we need a labeled data set. We need a labeled data set. So we have to convert our time series data into a labeled data set. Labeled data set means we have X values and we have Y values. So here, the given single column data can be converted into two column data in this particular example. Two column data. We can convert it as a three column data or four column data. Any format we can convert the data set. And in this case, we can convert into a two column data format, that is like a table where the first row of the table can be interpreted as, for example, data of 1, 1, first row, first column. And that represents this month's passengers, this month's or teeth time passenger information. And data of 1, 2, that is the second column information, and that is data of 1, 2, that is the next month, that is the t plus 1 passenger count that is to be predicted. Okay, but here the first column containing this month t passenger count, and the second column containing next month means t plus 1 passenger count that is to be predicted, that is to be predicted. So in this format we have to convert the data set, and this is a very important activity in order to work with LSTM. And this can be computed with the help of a user-defined function, and the function takes two arguments. The first argument is data set, which is a NumPy array that we want to convert into the data set. Then look back, that is another parameter, which is the number of previous time steps to use as input variables to predict the next time period. And in this particular example, this look back is initialized to 1, and this look back can be considered as a default argument in this user defined function. Okay, look back is equal to 1, and in order to take the prediction, just previous data value is used. Okay, and if look back is equal to 2 previous values are used for taking the decision, that is t minus 1, then t, then t plus 1. Look back is equal to 3 means t minus 2, t minus 1, t, then t plus 1. Okay, and in that way, in that case, if look back is equal to 3, the data table can be considered as a 3-column data table. 3-column data table. First t, then t minus 1, then t minus 2, then y. Okay, that type of a format is there, and we can analyze that. And this default value 1 will create a data set where x is the number of passengers at a given time t, and y is the number of passengers at the next time t plus 1. And in this format, we can convert the data. The time series data can be converted into a labeled data set, and that labeled data set is very important for processing using LSTM, because LSTM, as I said earlier, this is a supervised machine learning algorithm, and this is the user defined function. Convert an array of values into data set matrix. Definition: create data set comma look back is equal to 1. This is a default argument. Data x, data y, two matrices. For I in range, length of data set minus look back minus 1, a is equal to data set from I to I plus look back. Okay, I to I plus look back, and in this case 0 to 1, and that is the range in the first case. That is the first data is taken, first information in that sequential data is taken, and it is stored in A, and it is append with data x, then data y dot append data, that is the next value is stored in y, and for that we can make use of data set of I plus look back comma 0. And this process is continued for all the different data values contained in that CSV file or the sequential data. And after that, we can return these two matrices, data x and data y. And when we look into that particular x and y, and it will looks like this. That is x. These are the x values. This is unnormalized values. We already normalized for visualization. I just use the unnormalized values. Originally the data values looks in this format: 112, 118, 132, 129, 121, 135, etc. And after conversion as a matrix, the data values like 112 becomes x, and the next value becomes the y. This is t, this is t plus 1. Then in the next row, 118 becomes x value, and the next value becomes the 132 becomes the y value. And in this way, we can convert the given sequential data as a matrix, and for that we can make use of this user defined function. And that user defined function is very important, because that conversion is very important for processing the sequential data using LSTM. Let's use this function to prepare the train and test data sets for modeling. Right now, the test data set can be considered as a sequential data. Train data set is also can be considered as a sequential data. And both these data sets can be converted into a labeled data set with the help of the user defined function. And for that, here you can consider look back is equal to 1. Okay, for example, I just take look back as 1. You can take 2. So for taking the decision, 2 previous values are considered in that case. And look back is equal to 3. For taking the decision, 3 different previous values we can consider. And that is the speciality of this look back. Look back is equal to 1. Train x, train y, create data set, train, look back. Then test x, test y, test x, test y, create data set, test comma, look back. So here these are the x values. X values means the values of the independent variable, and this is the values of the dependent variable y. But here we have only one independent variable and one dependent variable. And look back is equal to 2 means we have 2 independent variables and 1 dependent variable, right? Okay, in that way we can convert the training data and test data as a labeled data set, Then again, one more very important information is there. The LSTM network expects the input data X to be provided with a specific array structure in the form of samples, time steps, and features. And this is a very dedicated format in order to work with LSTM. So our data is in the form samples, features, that is in the matrix format. That is a 2-dimensional format. But we have to convert that 2-dimensional format into a 3-dimensional format, because this format that is the default format to work with LSTM. And we can transform the prepared train and test set data into the expected structure using NumPy reshape. And there is a dedicated functionality to convert this 2-dimensional data into 3-dimensional data, and the functionality is known as reshape. But here number of samples means how many instances are there. Time step, how many time steps we are going to consider for taking the decision. And in this particular example, the time step is 1. And features, how many features? We have only 1 feature in this case. If the look back is equal to 2, in that case, how many features? 2 features. So in that way, by considering this information, we can reshape the data. So train x is equal to numpy dot reshape. Reshape is a functionality available in numpy train x, and we are going to reshape training data. And in this is the format or the structure I just used for reshaping. That is train x dot shape of 0. Shape that will give the information regarding how many rows and how many columns are there in the original data. Okay, but here shape of 0 represents the number of rows of the training data set x. Okay, then 1 time step. And train x dot shape of 1. Shape of 1 actually gives the number of columns of the training data x. So by considering these 2 information, or these 3 information, we can reshape. That means the 2-dimensional data can be converted into 3-dimensional format with the help of the functionality reshape. Similarly, test data can also be converted into this format. So numpy dot reshape text x comma test x dot shape of 0 comma 1 test x dot shape of 1. Now we are ready to design and fit our LSTM network for this particular problem, and the network has a visible layer with 1 input a hidden layer with 4 LSTM blocks of neurons and an output layer that makes a single value prediction. And this is the model I am going to use for this particular prediction. We have an input layer, and in that input layer we have only one input. We have only one input because we have only one independent variable, that is x, and four hidden layers. Sorry, a single hidden layer, having 4 LSTM blocks. So we have an input layer, we have a hidden layer, and we have an output layer. An output layer that makes a single value prediction. Here the prediction is only single value because the next time period prediction or next day's passenger value, and that is the prediction. That is only a single prediction. So this is the format of the LSTM network. And in this case, the default sigmoid activation function is used for the LSTM blocks. By default, I am going to use the sigmoid activation function. Similarly, we can use TANH activation function. And the network is trained for 100 epochs and a batch size of 1 is used. You can change the batch size as 16 or 32 or 64, etc. No problem, based on the total number of instances available in the data set. And we can create the model like this. Model is equal to sequential. An object is created of type sequential. Model dot add LSTM. Okay, LSTM. That means the first hidden layer and the input layer can be combined together with the help of this particular statement. In this sequential model, we are going to add a hidden layer consisting of 4 LSTM blocks with an input layer of shape 1 comma look back, 1 comma look back. And how many inputs are there? And that can be decided by decided with the help of this particular syntax. Input shape is equal to 1 comma look back, and in this case look back is equal to 1. That means 1 comma 1, only one input is there. Okay, then model dot add dense of 1. This represents the output layer. Output layer can be considered as a dense layer. Dense of 1 neuron is there. One neuron is there in that output layer. That is the significance of this one. And the activation functions are not specified. So by default, it takes the sigmoid activation functions. Otherwise, we have to explicitly specify the activation function by using the keyword activation is equal to. Okay, and here this is the structure. But here we have an LSTM network having an input layer, a hidden layer containing 4 LSTM blocks, and you can change, no problem for that. But how many LSTM blocks we have to use for a particular application, that actually based on the number of inputs, number of outputs, and how many instances are there in the data set. Based on that, we can decide the number of neurons for a particular model. And this is the output layer, only one output. And next is we have to compile that model. Compile that model means while defining a model, this model has some data structures for storing the weight values and so on. And these weight values we have to, or weight matrices we have to initialize. And that initialization operation is actually done with the help of the compile operation. This is also a dedicated method available in this sequential model. And along with that initialization process, we have to explicitly specify the loss function, and how we have to compute the loss. Loss is nothing but the difference between the actual value and the predicted value. And for computing that, which loss function we have to use, and that loss function we have to specify along with the optimizer. That means for weight updation, which optimizer? That means actually for weight updation, in this case, back propagation through time. That is the functionality used here. And in order to incorporate that functionality, which optimizer we have to use, and that optimizer is also we have to specify. And here I am going to use Adam optimizer. This is a very efficient optimizer. A number of other optimization functions are also available. You just verify what are the other optimizer functions and speciality of these optimization functions. So all these operations can be done with the help of the compile. Then in order to train the model, we can make use of another very important dedicated functionality, and that functionality is nothing but fit. Model.fit. And what are the parameters? Train x, okay, train y, epochs, how many times we have to repeat the process, that is epochs, batch size. And because actually the operation is batch by batch, And during the first batch, how many instances? During the second batch, how many instances? And here batch size is 1 means for each batch, because actually this is a distributed operation. And during the first GPU, for first GPU, how many instances we have to assign. For second GPU, how many instances we have to assign. For third GPU, how many instances we have to assign. So that actually determined by the batch size. And here I just use the batch size as 1. You can use the batch size as 16. That means at a time 16 different instances we can given to the GPU. Verbose is equal to 2. That means to see the status of the progress of the training. And in order to visualize that, we can make use of another argument, and that argument is known as verbose. So this is the statement that can be used for training the LSTM model. So model.fit train x, train by epoch is equal to 100, batch size is equal to 1, verbose is equal to 2. And once the model is fit, we can estimate the performance of the model on the training data. In order to evaluate the performance of the model, we can make use of the test data. And this will give us a point of comparison for new models. That means after the evaluation of the model, we get an information regarding for getting the output and what quality of output we can expect from that model. And that information we can generate with the help of testing. And note that we invert the predictions before calculating the error scores to ensure that the performance is reported in the same units as the original data. That means, and here all this processing, that is during at the time of training, the data value used for training is a normalized data value. But in order to compute the error, these normalized data values can be converted into actual data values, because min-max scalar is used there for normalization. And for that, we have to compute the predictions first. Here, in order to generate the predictions from the training data using the model, we can use a model.predict train of x. That is, all the predicted values corresponding to training data is generated with the help of this predict method, and all these predictions are now available in train predict. Similarly, all the predictions corresponding to the test data that can be generated with the help of model.predict of text x, and the predictions are now available in test predictor. Then all these predictions are in the normalized format. And in order to invert predictions, that is, in order to convert that predictions into actual data format, we can make use of an inverse transform. That is a scalar dot inverse transform train predictor. And that means this normalized data, now we can convert it into the actual data format. That is 112, 113, etc. That type of data can be generated with the help of this particular statement. Okay, similarly, train y is also converted into train y is also normalized. That can be converted into normal data value using inverse transform. Similarly, test predict is equal to scalar dot inverse transform test predict. Test y is equal to scalar dot inverse transform test y. So all the predictions and actual data values are now converted into the actual data format. And now, based on the actual data values, we can compute the efficiency of that model. Here, in order to compute the efficiency of the model, root mean square error, that is the metric used here. So that can be computed as train score is equal to math dot square root of mean squared error train y of 0, that is the actual value, actual decision, actual y value, and this is the predicted y value, train predict colon comma 0, all rows 0. This is a one-dimensional array. Okay, then based on these two arguments, we can compute the mean squared error. This is the actual value, and this is the predicted value. And that mean square error can be printed with the help of this particular statement. That means the error score. Error score can be error score corresponding to the training data. Error score corresponding to the training data, and similarly error score corresponding to the test data. And from the test predictions, we can compute the error by using the same statement with the help of test y of 0, then test predict 0 comma. This is the actual generated prediction, and this is the actual prediction. Then by comparing these two values, we can compute the test score. Okay, and finally, we can generate the predictions using the model for both the training and test data set to get a visual indication of the skill of the model. That means the test predictions and training predictions can be, we can visualize that predictions with the help of a by plotting that particular information. Because of how the data set was prepared, we must shift the predictions so that they align on the x-axis with the original data set. Once prepared, the data is plotted, showing the original data in blue, the predictions for the training data in green, and the predictions on the unseen test data in red. That means training, how the training process, how the testing is actually done in that model, how predictions are done, and all these things can be visualized with the help of a program segment. And this is the program segment. For that, I just use a shift train prediction plotting, shift train prediction, and because in order to plot the data in conformity with the actual data, we have to shift the train and test predictions, and for that we can make use of this particular statement. This is a set of statements used for display that plot. Display that plot. This is the plot used there, and from this plot, how training occurs, how testing occurs, and what is the actual data, the visualization of the actual data. All these informations are available in this particular graph-like structure. And we can see that the model did an excellent job of fitting both the training and test data set, because training and test almost in the same fashion. That means this model works well. This model works well, and in order to generate this particular visualization, I just write some statements, and with the help of these statements and the visualization facility available in Python, we can visualize this graph. Okay, and you can color, you can change the color of this model, no problem. Graph red, green, etc., etc. We can change that color. By default, this is the structure of the graph. And next is this is the last one. How to predict a new unseen case. That means at the time of executing this particular model, we have a prediction. Okay, here the last row of that test prediction, we get for a time t, we have a prediction, and time t is today's date, and what is the next day's prediction? What is that? That information is available in the test prediction as the last row of that particular table xy. Okay, or in that y we get the last value, and that last value becomes the prediction. And when we input that last value to this model, it will predict the next day's prediction. And for that you can use that. That is, new unseen case prediction can be done like this. Y is equal to test predict -1. -1 means from that test predict we can access the last value, and this value can be given to the model as a new input. And for that, first of all, we have to reshape that. That is y dot reshape -1. That is, add a new column. That is y dot shape of 0, comma y dot shape of 1. Y dot shape, that means here we have this test predictor. That information can be considered as a single element. Single element means in a matrix format, we have a row number, we have a row column number, and that row number and column number becomes that is a single element, right? 1 1. Okay, here -1 1 1. That using that, because the input, this input can be given to the model by considering 3 different dimensions, as I said earlier. Okay, and this is the method that can be used for adding a new dimension, that is -1, y dot shape of 0, y dot shape of 1, and next y can be computed like model dot predict yy, and what is the prediction corresponding to this new value. And in order to predict that, we can use this particular statement, model dot predict yy. Okay, and we can print that value by using print in xy. But here the problem is, this printed value is in normalized format. And in order to this is the output, that is 111. That is the shape. You just leave that information, and this is the value predicted there, 1.8958311. Okay, but this is a normalized value, right? Normalized value, and that normalized value can be converted into the actual value with the help of, as I said earlier, scalar dot inverse transform next y. So this is the actual value, that is 1086.0405, or in general it can be considered as 101086. That becomes the next day's prediction. Similarly, we can predict any type of information from this model. But this is the case with long short-term memory, and it is a very important model for processing the sequential data or time series data. And 2 days before, I just developed one model, and with the help of that model, we can clearly predict the COVID patients information. Like if we are inputting the 2 days affected patients, how many patients are affected from the CM's meeting, and my model will automatically predict what how many COVID patients we can expect in the next day. And that type of information we can print with the help of, or we can generate with the help of this LSTM model. You just try for that, and thank you for my patient hearing. Any doubts you can ask, no problem. Okay.
Thank you, sir. Now it's time for the queries. If any of the participants have any queries, you can post it into the chat box. So there is one query.
Yes.
For classification problem, also can we use RMSE?
RM?
SE.
RMSE, okay. Root mean square error for classification problem also we can make use of this RMSE, no problem for that. And normally for classification problem, as a common metrics, we always use accuracy. But at the same time, RMSE is also we can use, no problem for that.
Any other queries? Okay. So one more question is there, whether epoch and batch size related.
Batch size is actually based on the architecture of the system. We are going to work with this LSTM model. Okay, how many the structure of the GPU architecture, how many GPU cells are there, and based on that we can decide the batch size. And epochs actually normally we randomly give the epochs, but the common approach is we can execute the model. We can execute the model with various epochs. But after some epochs, the model converges to an optimal value. And by understanding that epoch number where the optimization occurs, we can finalize the number of epochs for the final model.
Okay. No other queries have been posted in the chat box. I think we have covered all the questions. So I would like to extend our sincere gratitude to Dr. Sabu M K for this fruitful and informative session. We actually live in the era of neural networks, and your presentation gave us an insight about the wide scope of neural network and its extensions like long short-term memory networks, especially in sequential data processing. Thank you, sir. Thank you so much.
Anyway, thank you for giving this opportunity for present my views. Thank you
Okay,
once
sir.
again. Okay.
Okay. And I thank all the participants for joining us. By this, our morning session comes to an end, and we'll be back with the second session for the day by 2 p.m. sharp. Thank you.